Okay, the lecture was cut short by the weather conditions, so I decided to do the last part of the lecture on video. So this is the part about laws and different theories of laws. I still during lecture said something about the different properties of laws, suggested properties of laws like universality, necessity, etc. So you can read that also on the slides. Where we ended up was to start talking about the different theories of law. It turns out that in fact all these theories can be derived from Hume's definitions of causation. We discussed these definitions of causation, two of these three at least, during the first lecture, so you may want to look at the notes of lecture 1 again. The first definition of causation was that of constant conjunction. So the idea was that you have an object, so that's a quote by Hume, an object followed by another, and where all the objects similar to the first are followed by objects similar to the second. So, right, that was the billiard ball example, one billiard ball, another one, the first being hit and taking off. If that happens constantly, right, all objects similar to the first being followed by objects similar to the second, we will talk about the first billiard ball causing the other to take off. Constant conjunction, so that we mentioned in lecture 1. And it turns out that this is actually the basis of simple regularity theory. The regularity here being regularity theory of laws, the regularity being here this constant conjunction, right? So the idea that laws consist of a single simple regularity that you observe in nature. Second definition of Hume that is labeled by Ehrman in the article Felt determination. The definition said causation is an object followed by another and whose appearance always conveys the thought to that other. So here it's psychological, right? What one thought the thought that's being conveyed, the first billiard ball hitting the other, conveying the thought of the other billiard ball taking off. We also mentioned that in lecture 1, and this is something that leads to the epistemic regularity theory. There's still a regularity, right? Something that happens regularly. But it's now psychological, or in this case, epistemic, right? It has to do with what I think of. And so this is the basis of regularity theories of laws, which take account of this epistemic aspect of the situation. Finally, and this one I think we did not mention, there's also, Ehrman points out, a counterfactual definition of causation in Hume. The quote, an object followed by another, where if the first object had not been, the second never had existed. Right? If something had not been, the second never had existed. So, right, had not been, it's counterfactual. It's a counterfactual statement, and this counterfactual reasoning I mentioned during the lecture also is related to lawhood as well, and in this case it can be seen as the basis of a third kind of approach to laws, and that's been called the necessitarian approach, or a necessitarian theory of laws, and Dretski's theory we will discuss is an example of this. So, point is, we end up with different accounts of lawhood. The way I categorize it in this lecture is in two broad sets of theories. Regularity theories on the one hand, in various versions, simple, epistemic, objective, I will talk about. And on the other hand, necessitarian theories like Dretski's universals theory, we will also discuss. So let's get into each of these theories. Starting with the most simple one, the simple regularity theory. This is, when you talk about theories of lawhood being associated with David Hume, this is the one they usually mean. Although, as I just said, you can associate all these different theories, trace them back to Hume, but this one really is considered to be the Humean theory. What does it say? Well, in the simplest form it says What are laws? They are true universal generalizations which describe what actually happens in the world. So two aspects: they're true universal generalizations, that's one thing, and that they're describing things that actually happen. Remember, Hume was an empiricist, right? He was very skeptical of the world containing causes and things like this, so he wanted to stick to observations, the things that sense perceptions in every respect. So the basic regularity theory denies that there is any objective, non-logical necessity that connects elements that are connected, that the law mentions. What makes something into a law is simply that all instances described by the law in the past, present, and future are true. It's simply what actually happens in the world that's being described, and it's true and universal statement. Examples. Well, all copper conducts electricity. What that means is that all copper in the past, present, and future will conduct electricity. All metals expand when heated, similar kind of story. Right? It's just a regularity in the world that we observe this. It describes what actually happens in the world. It's true. It's a generalization. It's universal. It's not specific to time and place. So that's what the theory says. Simple regularity theory. Now, as with all of these theories, there's various problems with the simple regularity theory, and 4 of which I want to briefly mention here. The first is the problem of vacuous laws. So the form of these laws here, you can say, is the form all X are Y, like all coppers, X, conduct electricity, are electricity conducting, you might say. Right? But what if there are no X's? Now, of course, we know they're coppers and they are metals, so that's not the example you should think of. But what about an example like all perpetual motion machines weigh 1 kilogram? Or all mermaids eat hamburgers? Or all particles traveling faster than light are red? In each of these cases, we assume that the X in this statement, so like perpetual motion machines, mermaids, particles traveling faster than light, all these things don't really exist. Still, logically speaking, the statement is true, and it's not only true, it's true everywhere. It's a true universal generalization describing what really happens. It's just so that the X that are being described, they're not existing, so the all X are Y statement is true because, yes, indeed, all mermaids eat hamburgers because there is no mermaid, similar with the other examples. So these are vacuous laws because they do not apply, right? Right, okay. Now, this problem, you might say, can get fixed easily because you might say, well, let's just say that laws are indeed of this form all X are Y, but that we also have to add the extra stipulation that there exists at least one X, right? So the 3 examples, the mermaids eating hamburgers and the perpetual motion machines weighing 1 kilogram, the perpetual motion machines, these are all excluded because there is no such thing as a perpetual motion machine and there is no mermaid, so the problem is solved, right? Okay, this would solve the problem of vacuous laws. However, this solution creates other problems, namely the problem of non-instantial laws. So that is the problem of non-vacuous laws which do not have any instances. So take the example of Newton's first law of motion. That was mentioned during the lecture by one of you. It states roughly that all bodies on which no net external force is acting either remain at rest or move at uniform velocity in a straight line. Once again, Newton's first law of motion: all bodies on which no net external force is acting either remain at rest or move at uniform velocity in a straight line. Why? So, strictly speaking, this is an example of a law without instances, a non-instantial law. Why? Well, here on Earth, we have the case that on all bodies, gravitational pull is active. So we can assume that in fact there are no bodies that are really free from net external forces. Right? So the condition that the law states, all bodies on which no net external force is acting, actually leaves no possible object to which the law applies. So the law does not, in fact, strictly speaking, Newton's first law of motion has no instances. Similar kinds of examples, all lumps of plutonium weighing more than 1 million tons conduct electricity, right? Also non-instantial laws. So the solution we just had to the first problem, namely saying that there must also be an X, right, creates problems here because there is no body on which no net external force is acting. So we have a problem with non-instantial laws. Possible solution of this, well, you might go now to counterfactual reasoning, right? So you could say laws describe not how objects do in fact behave, but how they would behave if they existed. So if there were indeed a body on which no net external force was acting, then it would remain at rest or move uniformly in a straight line. So that would be a solution. The only problem is this is very much against the Humean spirit, who was not a fan of counterfactual, because it describes situations which we precisely don't observe. I mean, things we don't observe happening in the world. Right? So this move to counterfactual reasoning and conditionals is one that's very much against the spirit of the simple regularity theory, and in any case would require complicating the theory quite a bit. Third problem, the problem of missing values for functional laws. So that's the problem that there are values of functional laws which never occur in reality. So you have many laws, of course, in physics which are described by equations, and where we know that not all instances of this law are actually observed. So take Hubble's law that says that it's about astronomy, that says that the velocity with which galaxies are moving away from each other is directly proportional to their distance apart. In this case, these variables, as is usually the case with mathematical laws, they range over an infinite number of values, right? You can plug in any number for these variables, and only a very small finite number of these possibilities will ever really be realized. So such a law actually does not describe what actually happens in the world, because most of these instances, with most of these values, this actually never happens in the world. So also there you could say, well, maybe we can move to counterfactual reasoning, right? Counterfactual reading of such a law. You know, if galaxies were at such a distance apart, then the velocity would be such and such, right? But that again leaves us with the problem of having to have a theory of counterfactuals and the non-empiricist aspect of the solution of the problem. Last problem, number 4, accidental generalizations. How to distinguish real laws from accidental generalizations. So that also applies to this example I still mentioned during the lecture of the distinction on slide 13 between, on the one hand, the sentence, all solid spheres of enriched uranium have a diameter of less than 1 mile, and the sentence, all solid spheres of gold have a diameter of less than 1 mile. So the first one being a law and the second one not. Why is the one a law and the other one isn't? The one about the sphere of gold seems to be somewhat accidental, and if that isn't accidental enough, you can come up with other accidental generalizations, like a nice one that a colleague of mine once came up with. Suppose it were in fact the case that all people who keep their oranges in the freezer have sweaty feet, right? Even if that were the case, we would not consider this to be a law, but rather to be an accidental generalization. That happens to be the case, but that does not fulfill the status of lawhood. But since it's a regularity and it describes what actually happens in the world, the Humean simple regularity theory would have no reason to outlaw the law, to say that this in fact is not a law. So people have thought to come up with some more sophisticated version of the regularity theory, sticking to the idea that lawhood has something to do with regularity. And so the first upgrade of regularity theory is then under the name of epistemic regularity theory, associated often, for example, with A.J. Ayer. And so here the idea is, yes, a law is indeed a true universal generalization, say G, but we need to add something extra. And the question is, what is the extra thing that we need to add? In the case of the epistemic regularity theory, the extra conditions are epistemic conditions. So they involve our beliefs and epistemic attitudes. And as it turns out, they're able to also handle some of these problems mentioned before, but what epistemic conditions are we thinking of here? So, for example, you might say that for something to be a law, it doesn't only have to be a true universal generalization, but it also has to be something that we are willing to use to make predictions, also for counterfactual situations we have not observed yet. Right? So say physical laws like Newton's law, we actually use to also predict things about objects that actually we haven't observed yet, but if we were to observe them, we would use the law to predict certain things. Furthermore, we accept it as well confirmed, right? That's also about an epistemic condition. It says something about our acceptance of something, right? It plays a role in the deductively organized system of scientific statements. It plays a role in scientific theory, so that's already part of something that is getting more emphasis in the next few that we get, so I'll skip this at the moment. And we recognize that it explains its instances. So we observe the instances of the law and we say, yes, these instances of the law are explained by the fact that there is such a law. Still, this epistemic regularity theory has some problems, and the main one really is that is the charge that it confuses epistemology, which is captured in these epistemic conditions, and ontology, the way things are, right? And this is related to something that I mentioned during the lecture, namely that even if we lived in a world completely without human beings, the laws of nature would still hold. So the fact that there is no one who is willing to make predictions using the law. There is no one who recognizes the law at explaining its instance. So the fact that there is nobody who could satisfy these four epistemic conditions that you see here listed as A through D does not change at all the fact that this world may have laws of nature, because the laws of nature are an aspect of the world's ontology and they have nothing to do with epistemological considerations as the ones listed here. Right? So the charge is the epistemic regularity theory confuses epistemology and ontology. So let's look at another version of the regularity theory, and this one goes under the name of objective regularity theory. And in fact, it's one that Ehrman, who you're reading a paper from for this part, is partial to, right? This objective irregularity theory is usually associated with the names of David Lewis, Frank Ramsey, John Stuart Mill. Because of that, sometimes also called the MRL theory of lawhood. What does this theory say? In a nutshell, it says a universal truth is a law. So you see here in this first part that the theory sticks to this notion of a regularity, right? Because candidates for laws are still universal truths. A universal truth is a law if and only if it belongs to the best deductive system from which everything that happens in the world can be deduced. So the idea is that laws are not things that you have to consider in isolation, but they are part of a bigger system, a scientific theory, you might say, from which you can derive or deduce the phenomenon that you want to explain. And something is a law if it's, you might say, part of the axioms of that system. And the system here has to be the best deductive system that allows you to deduce everything in the world that you're interested in. So note that the notion of a law now is relative, because what a law is may change, given that what our best deductive system is may change. So if, say, the first law of Newton is now considered a law, that is maybe because we think that Newton's other laws are the best deductive system describing phenomena. But if that changes, say because we now think an Einstein-like relativity theory actually describes things in a better way, and the axioms of that new theory do not contain Newton's first law, then that new Newtonian law ceases to be a law. Note also that this definition, in contrast to the previous one, is not epistemic, so it's taken seriously the charge that we should separate epistemology and ontology, because it's not about what we believe or think, because the notion of a deductive system is something strictly part of logic. No epistemic considerations enter here. So the separation of epistemology and ontology has actually taken place here. Further comment, what does best deductive system here mean? It should be simple and it should be strong. So simplicity, maybe as few axioms as possible, simple axioms. And strength, on the other hand, is that it should be able to deduce all the relevant phenomena or facts that you want to deduce. So those are the criteria for being the best deductive system. Criticism of this view. Of course, a criticism that I think we may have had earlier already in other contexts. Simplicity is a rather vague notion, right? I mean, few axioms, okay, you can count. People don't disagree that 2 axioms is fewer axioms than 3 axioms, but what if the 2 axioms are much more complex than the 3 axioms, right? What then is more simple? Second, how to balance simplicity with strength. So is a simple axiom system but weaker, is that better or worse than a more complex axiom system but stronger, right? So whenever you have 2 dimensions, how do we evaluate these dimensions with respect to each other? Third point, this seems to suggest that the best deductive system may actually be language dependent, right? So deductive systems, so axioms or formulated in a particular language, they are indeed language dependent, because one axiom system may use certain concepts and another axiom system may use other concepts. And depending on which concepts you use, which language you use, the deductive system may also be different. So what that means, the best deductive system may also be different. So what that would mean is that our notion of lawhood actually depends also on the language we formulate our system in and the language we formulate these laws in. And that seems a bit strange, because just as we would not expect epistemology to have anything to do with lawhood, it seems that the language we use to formulate our laws in should also not matter in what counts as a law or what doesn't count as a law. Finally, and that's a bit the lead into the last approach, aren't laws really something over and above a description of particular cases? In all these regularity theories, the idea is that the law really just, in a sense, describes or summarizes particular instances in a convenient generalization. But especially the problems with the regularity theory are things like accidental generalizations. These seem to suggest that laws really capture something deeper than simply regular cases, regular particulars. Shouldn't these laws really capture something about the necessary connection between events. The regularity theories in general say no, but the next theory we will discuss says yes. This takes this criticism seriously. So now we're moving from regularity theories to necessitation theories, things that try to capture this necessary connection between events that is supposed to underlie laws. The theory I want to discuss here is one associated with Fred Dretske, and it's called Dretske's universals theory. And as I said, it's one theory that tries to capture this notion of necessitation and make that the basis of lawhood. So what does this theory says? A law of the form all F's are G's, like all coppers conduct metal, in the regularity approach, we associate it to mean that all F's are G as a statement about particulars. All particulars that have copper, the property of being copper, have also the property of being electricity conducting. Dretske says what a law like this really says is not about particulars, but it's about universals. Namely, it relates Fness, copper conductingness, say, with another universal, namely, copperness, with another universal, namely, electricity conductingness. Laws, according to this theory, state a relation between universals, between properties, like electricity conductingness, copperness, right? They're about properties and not about individuals. And or another way to phrase this is to say that laws are singular statements about universals rather than universal generalizations about particulars. So this statement that you see here, Fness implies genus, is a statement about properties, about universals, like, F having the property of F. And they're not about particular objects. Now, this is a bit of a complicated point that I'll try to elucidate a bit more by introducing a distinction that is very important in this context, namely the distinction between extension and intension. The extension of a predicate is simply a list of all those objects satisfying the predicate. So if I wanted to give you the extension, say, of the predicate University of Groningen student, how I could tell you the extension of this predicate is simply to give you the names or ID card numbers or something like that of all the individuals that are University of Groningen students. Right? I give you the extension of the set of list of all the individuals satisfying the predicate. This is different from the intention, because you might say, if you ask me, well, what does it mean to be a student of the University of Groningen? You would not be satisfied if I give you just the list of all these students, because you would say, no, I don't want you to tell me who these things or objects or people are. I want to tell you what it means to be a student of the University of Groningen. And that is a question about the intention, the meaning of the predicate. Now, obviously, maybe not so obviously, two predicates can have the same extension without having the same intention. An example of this is, apparently, I'm told, that it turns out that mammals, among the living beings, mammals apparently are also the beings who have hair. So, hairy living beings, the predicate of hairy living being has the same extension as the predicate mammal, right? Because the same objects are mammals as have hair, as the objects are the same creatures who are mammals are also have hair, and vice versa, so they have the same extension. But obviously, mammalness, the property of being a mammal, means something different from having hair. Now, so this distinction between extension and intention, the reference, the extension, and the meaning, the intention, this difference is important for Dretske's theory of law, because Dretske says laws are about intention and not about extension. How does this turn out, or how does this play out in his theory of laws? Well, because laws are about intentions, this also means that laws are opaque. So look at the following example. All mammals have mammary glands. Mammary glands are the glands that mammals use to give milk to say, offspring, right? This, right, Dretske would claim, is a law, right? A law of biology, maybe, right? All mammals have mammary glands. Now, as I said, we can, if we now assume that mammals are precisely the creatures that are hairy, precisely the animals that are hairy, the extension of mammals and hairy animals is the same. Now, if you substitute in the law all mammals are have mammary glands, if you substitute in this law mammals by a predicate with the same extension, namely hairy animals, you get the statement all hairy animals have mammary glands, which is also true. After all, mammals are the hairy animals, right? So if one is true, the other is true. However, and that's the important point, Dretske would claim, the result of this substitution is not a law. What is a law is only the first statement, but not the second. And this is the property of opaqueness of laws. Laws are opaque, which means we can substitute predicates with the same intention, but not predicates with the same extension. So if you have a law and you substitute another predicate with the same extension, you may lose lawhood. You have to substitute a predicate with the same intention. So in this case, it would mean substituting something from mammals that has the same meaning as mammals and not just coincidentally the same extension. Okay, let me, before I go to that, note that this problem, or this property that you start with a law and you substitute something with the same extension and you don't have a law anymore, this is something that the regularity theory cannot easily account for. Why? Because on the regularity count, both are just describing regularities. And of course, the regularity that mammals have mammary glands is the same regularity as the regularity that hairy animals have mammal glands. So there's no difference here, whereas there is a difference in lawhood. It turns out that this approach solves actually the problems of the simple regularity theory. So for example, contrary to fact possibilities are covered. So there's no problem with non-instantial laws. So remember the example of a law that refers to bodies which have no net force acting on them, right? So that was a law about bodies that don't actually exist. This is not a problem here because the laws under the universal theory, they're not about particulars, not about objects that have no net force acting on them. They are about a particular property, the property of having no force acting on you, that property is related to something else. So the whole issue of counterfactual reasoning is very easily working with an account of laws that works with universals rather than particulars. What's a problem for this account is that the arrow here between F-ness and G-ness, right, is really not explained in the theory, meaning it's not clear exactly what Dretske means by when he says that F-ness has to imply, yield, bring with it G-ness. This necessitation is what's called usually nomic necessitation, nomic from nomos law, right? It's a necessitation associated with laws. But what exactly does it mean when we say that F-ness necessitates G-ness? Necessitation in what sense? Right, when I discussed earlier during the lecture the issue of what necessitation means, I said, well, it could be logical necessitation, it could be physical in some sense, but what does that really mean? how would we determine such a necessity, right? The determination of that necessity raises Hume's initial worries of empiricism. If somehow it means necessity, that somehow in all physically possible worlds one thing implies the other, well, how can we investigate that? We cannot just conjure up all possible physical worlds, and because we only have the one that we live with in, right? So as an empiricist, this whole idea of necessity is very suspect. An empiricist like Hume would say that there's only one kind of necessity, and that is logical necessity. But gnomic necessity hardly seems to be the same as logical necessity, because that would make all laws of nature logically necessary. But there's no reason to assume that something like Newton's first law of motion is logically necessary. We could easily imagine a world where that law does not hold. So that seems too strong. So what then is this gnomic necessity? Well, Dretske would probably, some advocates of the universal theory have claimed that this notion of necessitation is so basic that it has to be treated as a fundamental, inexplicable, basic concept of the theory that cannot be analyzed further without running the risk of regress or circularity, just like induction is so basic that it cannot be further justified without turning around in circles. Others feel that that is too easy a way out, that we should say more about what this arrow, what this implication or necessitation of F-ness towards G-ness really means. Okay, so much about the accounts of laws. Well, if we had now been in the lecture hall, I would have asked you what account of laws actually applies best to the law that you may encounter in your fields. What view do you think is actually correct for the laws that your field discovers or treats? Remember, in the lecture we had Newton's first law of motion, we had the supply and demand law from economics, and we also had sort of acoustic laws from music about A minor is parallel to C major, what that means, well, you will, unfortunately, due to this video lecture, have to think about these examples and what you think works best as an account for these examples. You have to think about that for yourself. Finally, we discussed the life world in the first part in class, and here I said something about laws. I said you can see these as two separate topics, but I want to close also with a bit on the connection between these two and from the perspective on Husserl, somehow going back to the beginning, closing the circle, returning to the beginning. And I want to do this with this one quote, which is in the Husserl piece, which actually is a nice way to draw this to a close and to connect the life world discussion with discussion of laws. Husserl writes, by contrast to the universal causality of the intuitively given world, Galileo discovers what has since been called simply the law of causality, the a priori form of the true, idealized and mathematicized world, the law of exact lawfulness according to which every occurrence in nature, idealized nature, must come under exact laws. So as I mentioned during class, right, Husserl, he talks about nature, the mathematized nature, right, not nature as we experience it in the life world, what science makes nature into, what science makes nature to be. And Husserl says that what comes under laws is not nature, but nature, right? So when we talk about laws of nature, what they're describing is not our direct life world, but what they're describing is the natural world as it's conceived in a particular science, the abstracted, idealized version of nature that science gives us. That doesn't make the laws any less powerful when it comes to prediction, technological advances, etc. It just says that on a Husserlian view of life world and the difference between life world and science, the laws of nature are really laws of nature, of not the life world, but of nature as it's conceived of by science. Summary. Well, of course, the two parts, what is a law of nature and what's the relationship between life world and nature. What is a law of nature? Well, we see that there's different theories. We could say law of nature is a regularity, a true universal statement, plus with some extra conditions, be they epistemic, maybe the deductive system condition that they're part of a general deductive system. The necessitation view would say maybe a law of nature is a relationship between universals, between properties, right? F-ness being related to genus, copperness being related to electricity conductingness. And there's other views which we did not cover, that the law of nature might be a description of a tendency or of a behavior of an object, that we did not cover. What about the relationship between life world and science? Well, it depends on what you mean by science, right? Depends on, we talked about native science on the one hand and Western science on the other hand. Native science tries to be direct extension of the life world, and in a sense you might say tries to fulfill part of the Husserlian program of a new kind of science that tries to capture more of the actual life world. On the other hand, modern science is a science that produces laws, presents a kind of knowledge that's severed from the life world, so you might say that Husserl somehow is able to make sense of this distinction we discussed already in this course between scientific knowledge on the other hand and other kinds of knowledge. And Husserl wants really a kind of science that actually takes better account of subjectivity and phenomenological considerations of the subject that does the knowing. So he thinks another science is possible and should be developed. And although he is not very concrete about what that science should look like, you might think that native sciences, aboriginal epistemology, these kinds of ways of being in nature, midwife knowledge, are examples of go at least some way towards what he had in mind. Next question, next time. We will discuss the topic of realism versus anti-realism. Do claims about non-observable entities that are made in the particularly natural sciences, like say claims about electrons, how do we need to interpret these claims in a realistic way or in an anti-realistic way? So, of course, we'll discuss what realism and anti-realism is and what the arguments for these positions are, and how to interpret claims, for example, about electrons. Do they have a truth value? Can we come to know it? And how do we have to read these statements? This is the reading list for next time, and I hope that even though that you all made it home safely in spite of the weather conditions, and that you can actually have a look at this video, and at least if you have questions, you can bring them to class next time, and we will also have a review session anyway where you can ask questions about this video lecture.